Okay, so previously we talked about elution, LUTs, flow rates, and the whole concept that if you crank up the pressure too much, you're going to stop popping the tubing. And you don't want that to happen, right? Okay, so we're going to clear this out for a second. And I need to go back to this concept of components coming out of the bottom of the column. All right, so here's the column, and I see drip, drip, drip. And then down here below, I have a collection flask that I'm collecting the things in. Now, the same thing happens in instrumentation. It comes out of the column, drip, drip, drip. And then down here, the collection tube basically is fed to a detector first, and then it goes into the waste jug after that. So what I want to focus on here is the concept of things coming out. If I put things in, things have to come out, right? That's very, very important. So in the chromatogram, what you often see is a peak that comes up and then comes back down. And that's what we would call the peak of the chromatogram, okay? The question that some people have is, if things are coming out and they're supposed to come out all at once, then why don't they just kind of come straight up and straight back down and then do that number? Well, actually, they are supposed to. Okay, but rarely do we see a chromatogram that looks like this, that's made up of peaks. But this is kind of the more common that we would see in a laboratory. The closer we can get to the second one, though, this is really what we're after. That's how a chromatogram is supposed to look. So there's got to be some questions on why do certain chromatograms look the second version, and why do some chromatograms look like the first version? What can we do to make the second version show up more often? What kind of settings can we tinker with? What can we do to our samples? And is there anything at all that we can do to completely eliminate the problem and get the second version every single time we run a sample? So what we're after here is something called a Gaussian shaped peak. And if you've taken a statistics course or a math course, you might have seen the word Gaussian before. And sometimes they actually talk about it in biology as well. So a Gaussian shaped peak just basically means even. All right. So you basically have a center, and it comes down off the left and it comes down off the right. And if you take the peak and you divide it up in half, then half A is exactly equal to half B. That's what Gaussian shaped peak is. The problem is that not every single time do we get a Gaussian shaped peak. So it doesn't matter if we're after this kind of peak that shows up in our lab or this kind of peak that shows up in a lab or textbook. Whichever route that we decide that is acceptable, both of these should be Gaussian shaped, which means that I should be able to split this peak up in half and have the left match the right, and I should be able to split this peak up in half in a very narrow sliver, and the left should match the right. Okay, so no matter which way we go, these should be Gaussian shaped. The problem is that sometimes these things are not Gaussian shaped, and there's maybe certain things that we can do to alleviate those problems and to maybe fix it better on another run when I repeat the measurement. All right, so why are things not Gaussian shaped? Well, number one, we talk about an irregularity. Irregularity in the concentration in the injection zone. So previously in a video, I've talked about this concept of making sure that your sand level was flat. And then I said you allow your mobile phase to go and seep all the way in, and then you allow your sample to seep all the way in. All right, well, if the sample is injected into the top part of this column, and let's say that it's not injected that particular way, but let's say there's a disturbance up there. It's not all going in at one time. Or let's say that there's an air bubble or an air pocket up at the top. Or you didn't let the mobile phase go all the way into the column before you injected your sample amount. And your sample's gradually being introduced into the column instead of just all at one time. This is an irregularity in the injection zone. So what happens is that some of your sample will basically come out in the early stages, and that's what we see here in the first part of the chromatogram. And then the majority of the component is actually coming through now, and that's why you see this peak get a little bit fatter. Then when the majority of that peak or that component has went through the column and the peak has been formed, well, it starts to slow down. There's not as much in there anymore. So little by little, less and less product begins to come through the column, and you start to see this peak go down back to baseline, and then it will flatten itself back out again. But the irregularity in the injection zone is maybe what would cause these very wide peaks that begin to happen. Okay. We're also going to talk about peak shape in just a second, but for now we're only focused on why things take a little bit of time to come off and why my peaks are a little bit wider than they are really narrow, or maybe even just one line that goes straight up and comes straight back down. Okay, so number two, the other thing that could happen is that the speed of the mobile phase is slower at the edges of the column. So as my mobile phase goes through this column, it can rake up against the sides of the column itself, right? And this creates some friction. And that friction is going to slow down the flow rate of the mobile phase very slightly. And that disturbance and that slowdown is enough for the outsides of the column to be delayed a little bit longer. And that's another reason that we see option number 1 happen on my chromatogram and not option number 2. Things are getting slowed down on the outside edges, and because of that, they're not all going through at one time and just out the column, but I'm having to wait on them a little bit more. So band number 1 at the top, the little water band, begins to form, and we don't really get theory textbook ideas like band number 2 that sits down below. So the speed of the mobile phase at the edges of the column are a little bit slower than the middle. The middle part runs faster, and that gives me this kind of wider band that begins to happen in my chromatogram. Number 3, I have different flow paths. And there's nothing I can really do about any one of these 3, especially if it's on an automated machine. Now, what does different flow paths mean? Well, I need you to think of Price is Right, and I need you to think about the game of Plinko. So sometimes, if I've got a molecule or a component that's been injected at the top of the column, that component can basically go straight through and out the other end. That's one flow path. However, nothing says that that component can't play the game of Plinko and basically tick-tock all the way down the column and out the other end, which basically means that it can kind of come out here, and then it can kind of come over here, and then it can kind of just venture back and forth, and I'll see a different flow path for maybe every single molecule that goes through that column. And those different flow paths means that some molecules travel a little bit slower than the others in the same group. All right, so keep in mind, we're talking about the same component here, the same type of molecule. The same type of molecule should basically theory-wise, all cluster together and go straight out the other end as a cluster. And sometimes they start to spread apart. What is causing them to spread apart and giving us this wider peak in the chromatogram? Option number one is that the injection did not go all at one time. It slowly sucked into the column little bit by little bit, and that caused these things to separate a little bit more on me. Option number two is that your mobile phase goes a little slower on the edges. So because of that, those molecules travel a little bit longer to go out the other end, and I start to see a separation of the band. And option number three, different flow paths. There's different routes that these molecules can take inside of the stationary phase. And because of that variation, I see a wider peak than what I would want to see as far as theory or textbook goes. No matter the case, these things should be symmetrical, right? So these three options that slow my components down, that makes things go a little bit longer, doesn't matter. They should still be Gaussian shaped. It should still be a symmetrical peak. But this is one of the reasons that we start to see this band getting fatter and fatter and fatter. Now there is a term that we use here, and this is called band broadening. And band broadening basically means that this peak on the chromatogram is getting wider and wider and wider. So we want to control the band broadening. We want to make sure that it doesn't go too fat. We want to make sure that these things come off of the column all at once as much as we can. Band broadening is bad, and I want to stay away from that. But I have to make the assumption that I can't get away from all of it. Some of it is going to be present. And the reason that that's present is for the three reasons, the major reasons, that are down below. All right? So in the next video, we'll continue with this concept of Gaussian shaped curve. We'll talk about why things would not be Gaussian shaped, and we'll pick up from there and continue our lecture on these concepts now of basic chromatography and the actual chromatograph itself.